Sure thing. It's a lot out there. That's not what I want. Yeah, there we go. Hello. Pin my video. That. Here's the attendance form. If you need to leave a little early, that's totally fine.
What?
If you need to leave, you said you had a bio exam right after this?
Yeah.
You need to leave a little early, totally
Oh, I
fine.
did that. I meant right after this, as in an hour.
Oh, okay, sure. Fair enough.
Yeah, I did.
Good.
You- oh, no. It's such a like, so I only missed one, but right now I can stop doing the class and not even do the final exam and I would get an A plus. It's probably the same with you. It's yeah, because he dropped to a lower score and the last thing is that. Yeah, he said, well, no, I just watched the lecture. He said he didn't know.
Sure thing, Alondra.
I know, it's amazing. Yeah, no.
What class is that for?
This is for biosite,
Okay.
right? It's interesting. It's
Yeah.
sort of a bizarre class because the material is really hard and complex, but the actual assignment.
Forgot on my pen.
Right. It's a problem. And all the midterms are online.
Well, shoot. No pens in my bag.
Yeah, it's like, it's essentially like a psychology, but there's a big emphasis on neuroscience and.
Right, I made a fatal error here and I forgot to bring, oh, here's the pen I left from, these are probably terrible pens that don't actually work, the ones I left here for that, I was like, but well, I might have to borrow a pen from someone, we'll see. Let's get started though. What's that? Okay, I might need to borrow it. So, someone said, let's look at problem 5, so we can look at problem 5 or one like it. Oh, sure, this was already on my mind, so let's look at something like, I'm gonna change up just a little bit. We can totally talk about how we would do it differently. Let's say I have e to the 9x times tangent of e to the 9x. Yes. So if I was trying to do a problem like this, I would start with the u sub. I would start by letting u equal e to the 9x. There are other choices you can make, but that's probably where I would go first. So if we do that, we're going to get du equal to e to the 9x times 9 times dx. And if we solve for dx equal to du divided by 9e to the 9x. So something I want to point out about this one is, I was helping someone with this one earlier, and they did the following. They made a kind of a mistake that I want to caution you against. So I'm going to get e to the 9x times tangent of e to the 9x times my dx, which is du over 9e to the 9x. Now I need to cancel that e to the 9x on the bottom. It definitely is going to cancel. What does it cancel with? Or, well, sure, I asked a bad question. Which e to the 9x does it cancel with? Yeah. That one inside the tangent, it's stuck inside the tangent function. I heard someone describe it once as like the tangent or the trig function is kind of like a bodyguard. It's protecting the stuff inside of it. You can't get at the stuff inside of it because of that bodyguard. So that e to the 9x here has to cancel with that e to the 9x there. And then we're left with the integral of tangent of e to the 9x, which is my u. And then I've got a du over 9, but let's put the 1/9 out in front. Question?
You can't put as two different values, as two different times in the.
You can, but the thing is, we always have to make sure that this x in the denominator of your du thing has to cancel out. So it'd be totally fine to write this as the integral of u e to the u. Sorry, that's not right. U tangent of u times du over 9 e to the 9x. But then we have to recognize that e to the 9x is really equal to u, and that u cancels with that u there. So yeah, it's going to go away. And that's why I would emphasize before you start putting in things for like replacing things with u. I always really just want to deal with this part first. So this is always kind of the first thing we should deal with before we replace any of those other things with u. So that we can see what cancels, and then after we have canceled out what's in the denominator there, then replacing anything else that looks like u with u. Okay. So now at this stage, you kind of have a choice. Maybe not a choice, you have either you remember it or you don't. So if you remember what the integral of tangent is, great. But if you don't, which is plausible, my go-to, if I don't know how to do an integral with a trig function, is typically to write it in terms of sines and cosines. So I'm going to rewrite this as 1/9 integral of sine of u over cosine of u du. And then we're going to do a second u substitution. Since I've already used the letter u, I'm going to use a different letter. I'm going to use w is typically the second choice. If you've used u, w is kind of the next one we use. So I'm going to let w equal cosine of u. And my dw is equal to negative sine of u du. And then we're going to get 1/9 the integral. So again, I'm going to follow my own advice. Oh, I forgot to do the one thing, sorry. dw divided by negative sine of u is equal to du. I'm going to follow my own advice and replace just du with what it's equal to and leave everything else the same. So I've got sine of u over cosine of u, and my du is dw over negative sine of u. The sine of u's cancel. We're bringing the negative out in front. So I'm going to rewrite this as negative 1/9 integral of dw over cosine of u is w. Finally, we can actually integrate this thing. So do be careful. When you get to the stage, right, I've got dw over w, I can't just start putting back in what w is equal to. I've done all this work so that then I can actually do the antiderivative. So the antiderivative dw over w, or if you prefer, the antiderivative of 1 over w times dw is the natural log of the absolute value of w plus c.
I got confused on why we had to do the second u sub. Is tangent just, don't we just know that they?
Right. So some people might not remember that the integral of tangent is the negative natural log of the absolute value of cosine.
Okay.
But if you exactly right, so we're about to see that if you remember that the integral of tangent of u is the negative natural log of the absolute value of cosine of u, then you totally could have skipped the steps from here to here.
Okay.
And just gone straight from this to that. And then we still have to go back to our original variable, which was x. It's very loud outside. So it's going to be negative 1/9 the natural log of the absolute value of cosine of u, which was e to the 9x. Absolute value. Let's see. So that is essentially how you would do problem number 5. The only difference between my example and your example is probably that I think you have an e to the negative something, and you have a cotangent instead of a tangent, but it's very much the same idea. In that same sort of vein, looking at a problem similar-ish to problem 7. Oh, I don't have problem 6 on here. Do you guys have problem 6 on your homework assignment? That's interesting. Yeah, I have like 1, 2, 3, 4, 5, 7. Okay, interesting. Anyway, looking at one similar to problem 7, this is kind of where that same piece of advice is going to come into play. So, sure. Just do this. Yeah. So let's look at something not entirely dissimilar to, let's see, what have I got here? I want to make this look a little bit different. Sure. Sure. Let's say I've got like cotangent to the 8th of negative 3x over, they really made this really, really gross in my opinion. But that's fine. It's actually, I lie, it's not that gross. It sounds like, sorry, just it sounds terrible out there. Secant to the fifth of negative 3x times cosecant to the 9th of negative 3x. That looks sufficiently awful. And before I do anything, you might, although I don't think we really need to, you could do a u substitution letting u equal negative 3x. But that's not that big a deal. We know that instead of doing that, we're just going to end up dividing by a negative 3 at the end, probably. Okay. So here is where writing things in terms of sines and cosines is really to your advantage. So I'm going to rewrite this as the integral of, so cotangent is cosine over sine. So cotangent to the 8th is cosine to the 8th of negative 3x divided by sine to the 8th of negative 3x. Times, now dividing by secant, secant is 1 over cosine. So if you're dividing by 1 over cosine, you're really multiplying by cosine. So secant to the 5th here in the bottom is really like multiplying by cosine to the 5th. So we're going to multiply by cosine to the 5th of negative 3x. And then we're also going to, same thing, just like secant is the reciprocal of cosine, cosecant is the reciprocal of sine. So we're really going to have 1 over sine to the 9th, which is going to become just sine to the 9th. So just to make sure everyone's super cool with this, right? This secant to the 5th here is 1 over cosine to the 5th of 3x. And then we flip the multiplied. Similarly, cosecant to the 9th here is 1 over sine to the 9th. And so then I've got my cotangent, which is this stuff here, my secant, right? But dividing by secant is multiplying by the reciprocal. If you like, I can do that to make it a little more obvious. And the same deal for 1 over cosecant to the 9th is sine to the 9th. Questions about what we've done so far? Cool? Okay. Yeah, cotangent is cosine over sine, tangent sine over cosine. So then we simplify, right? The whole point of this was to make this not terrible. So I see a cosine to the 8th times a cosine to the 5th is a cosine to the 13th power of negative 3x. And sine to the 9th divided by sine to the 8th is going to be just a sine of negative 3x. So we have a choice. I will point out, technically either choice would work here, but one of them is much, 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 much worse than the other one. So the choice we want to make here is to let u equal cosine of negative 3x, because it's the thing that's stuck inside the being raised to the 13th power. If it's helpful, you can rewrite this as the integral of cosine of negative 3x raised to the 13th power times sine of negative 3x. Just to help you recognize that, oh yeah, you've got something raised to the 13th power. So then we're going to let u equal the thing that's stuck, and also the thing whose derivative is also in there. If u is cosine of negative 3x, du is going to be negative sine of my stuff times the derivative of my stuff, dx. Then we do the usual thing. Dx is going to be negative is positive. So I'm going to say dx is du divided by positive 3 times sine of 3x. Sine of negative 3x, sorry. Trying to keep numbers on here just so it's easier to find things later. Okay, so then after that, we just replace this. Again, if you're doing this the very careful way, you're just replacing dx with what it's equal to first and nothing else. So I'm going to write this as the integral of cosine of negative 3x to the 13th power times sine of negative 3x. And this pen depends. Make it last. Of negative 3x times my dx, which is du over 3 times sine of negative 3x. And as is typical, the thing that has a variable is going to cancel. I should say The thing that has a variable in the denominator here is for sure going to cancel out. That's always what we need to happen in a u substitution. The sine of negative 3x cancels with sine of negative 3x. And then we finish translating this into u's. This becomes the integral of u to the 13th divided by 3 times du. And the rest doesn't suck. We've got 1/3 times u to the 14th over 14 plus c. And then you plug back in what u is equal to end up with u, which is cosine of negative 3x. So you've got cosine to the 14th of negative 3x divided by 3 times 14, which is 42 plus c. That's your answer. Which if you think about, well, if you think about what you've got here, seems pretty reasonable. If you take the derivative of something to the 14th power, you get 14 times that something to the 13th power times the derivative of the inside stuff, which is negative sine of negative 3x times negative 3. And then the 14 and the 3 cancel out the 42. So it totally works. Questions about anything we've done here? Would like to say more about these types of integrals, but I just don't feel like it's not a great use of your time because I don't think your teacher is really going to ask you anything else. Like, for example, well, I'll do one example and then we'll move on. You could someday see maybe an integral that looked like, let's make sure it's not terrible. Secant to the 4th of x times tangent squared of x dx. We'll do one example. So this is just like your sine cosine situation, and that you want to pick u to be either secant or tangent so that your derivative also shows up. Here we have to be a little bit more careful because we still want the leftovers, if there's going to be leftovers, to be to an even power. Meaning, here's the wrong choice. If I were to pick u equal to secant, I would want the amount of tangent left over to be to an even power. That's not going to happen here though, because if u is secant, my du is going to be secant of x times tangent of x dx. And that tangent of x right there is going to take up one of those tangents there. And so I'm not going to be left with an even power left over. So that is the wrong choice. The right choice, I think, yeah, it is going to be letting u equal tangent. What's the derivative? And well, because my du is the derivative tangent secant squared dx. And when I deal with that secant squared, I'm still going to have another secant squared left over. And as long as there's an even power of the not u choice left over, we are safe, meaning we can use a trig identity. So let's see what happens here. This is going to equal the integral of secant to the 4th of x times tangent squared of x times my dx, which is, sorry, I didn't solve for it, du divided by secant squared of x. Okay, so then secant to the 4th divided by secant squared is going to give me a secant squared left over. So I'm left with the secant squared of x here. So then I've got the following. I've got secant squared of x. Tangent is what u is equal to. So tangent squared is u squared, and then du is still du. I'm not done translating yet. I still have x's in my integral. So this is where the reason we need an even power left over is so we can use a trig identity. And I feel like I must have said this in class before, but if I haven't, the best trig identity ever is I tan and get sexy. Unforgettable. I tan and get sexy. 1 plus tangent squared x equals secant squared x. I tan and get sexy. Student told me this one time. I've never been able to forget it as much as I've tried. It's unforgettable. So 1 plus tangent squared x equals secant squared x, or I tan and get sexy. We're going to replace secant squared with 1 plus tangent squared, but tangent is equal to u. So really we have 1 plus u squared equal to secant squared. So that's what's going to go in right there. So we're going to get the integral of 1 plus u squared times u squared du. And before we integrate this, we have to multiply it out. We can't just integrate each of these parts multiplied together. We have to distribute things out and get the integral of u squared plus u to the 4th, which is then going to equal u cubed over 3 plus u to the 5th over 5 plus c. And then we finally plug back in what u is equal to, which is tangent, and get tangent cubed x over 3 plus tangent to the 5th x over 5 plus c. But I don't think your teacher has really talked about any examples like that. Is that right? Am I correct in that assumption? Yeah. Okay. So I'm not going to, there are more examples in this same sort of vein, but basically if you've got powers of sines and cosines, or powers of secants and tangents, or powers of cosecants and cotangents, the idea is to let to do a u sub, to let u equal either sine or cosine, or secant or tangent, or cosecant or cotangent. And then you need your leftovers of your not u choice to have be to an even power. And then you can do a trig and need to get that. But again, I think we're probably not seeing much of that in this class. So I will stop talking about it because although it's neat, we should use our time effectively. All right, so let me ask you all, are there any other dire questions from the homework assignment from section 8.5? Asking people on Zoom, people in class as well. Man, there's not a lot of questions on it. I feel like we've covered most of them to some extent. Okay. So sorry, your water bottle is like a giant mustard container for a second there. Like, right? Does it kind of like a French's mustard? Like, I'm like, oh wow, that's a lot of, oh, that's not mustard, that's just water. Okay. So I would love for you all to be able to have the ability to start working on your next homework assignment, which is due, I don't know, like the 14th or something. Section, what is it, 6.3? Yeah. Partial fractions. So let's start off with an example that's not going to require partial fractions. Let's say we want to find, this is number 4, the integral of 2x plus 6 over x squared plus 6x plus 8. So if I was going to try that, the first thing I would think about doing is the first thing I usually think about doing when something's more complicated than just simplifying it. I'm going to look for a u substitution. I really can't say this strongly enough. When you're doing integration, after you've gotten past, I can't simplify this and just do it directly, the first place you should really go is, can I do a u sub? Is there a good choice for you or not? In this case, let's see. If I let u equal the bottom, because that's usually the choice if you've got fractions, my du is going to be 2x plus 6 dx, which is exactly the top. And I really feel like you could just, you don't have to do the thing where you say dx is du divided by 2x plus 6. You can just be like, hey, there's my du right there sitting in my integral. This is really equal to the integral of du over u. Or again, if you prefer, 1 over u du. We know how to integrate that. It's going to be the natural log of the absolute value of u plus c, which is the natural log of the absolute value of x squared plus 6x plus 8 plus c. And that's our answer. So sometimes when you're integrating a rational function like this, it turns out nice. Basically the derivative of the bottom is just equal to the top. Great, wonderful. We're happy about that. Sometimes, most of the time, it's not what's going to happen. So let's look at what seems like shouldn't be too much of a worse problem. The integral of 2x plus 5 over x squared plus 6x plus 8. Okay, so we already know from the work we just did, a u sub is not the way to go. Because if we choose u equal to x squared plus 6x plus 8, your du is 2x plus 6, and that's not what we have on the top. And there's not a really good way of manipulating it so that we get that. So instead, we're going to use a whole new method of integration, which actually, I should say, it's not a whole new method of integration. Really, the methods of integration are not changing. It's a method of rewriting using algebra, the thing we're integrating, so that it's something that's easier to integrate. So we're not actually doing anything special other than just using an algebraic technique to simplify this expression. So here's the idea, or actually here are the rules, for lack of a better phrase. To use partial fractions, you have to have a couple things being true before you get going. First thing has to be true, has to be a rational function. Rational function. Meaning top and bottom both have to be polynomials. Only positive integer powers of x, no fractional powers, no negative powers, and so on and so on. So the top is a polynomial, it's a linear polynomial, 2x plus 5. The bottom's a polynomial, x squared plus 6, x plus 8. Second thing that has to be true, the degree on the top must be strictly less than the degree on the bottom. I will also point out, if they're not, then we do polynomial division. If not, you start with polynomial division. And thirdly, and arguably most importantly, but not really, the bottom has to factor. So if those three things are all true, and you've checked to make sure you can't do something else that's easier, then integrate partial fractions is typically what we do. I often refer to partial fractions as a method of last resort because you want to try everything else before you do partial fractions. Okay, so the idea with partial fractions is, well, first we want to make sure this factors. So this does factor. I've got the integral of 2x plus 5 over x plus 4 times x plus 2. So the whole idea is that we can take that fraction whose denominator factors and write that fraction as the sum of two fractions with less complicated denominators. It's kind of like, although not exactly like, how you could take, sure, I'm going to make something up that's probably going to be stupid. It's fine. It's not fine. I should be careful. Sure. You could take the fraction 5/12 and write it as the sum of fractions with less complicated denominators. Probably. I pulled that number out of my head. Yeah, it should work just fine. Probably. Maybe. Let's do 7/12 just to make it easier. You can write that as some fraction whose denominator is 4 and some fraction whose denominator is 3. That's kind of the idea, is you're taking a fraction with a quote unquote more complicated denominator and writing it as the sum of two or more fractions whose denominators are less complicated but multiply to that denominator there. Who are factors of that denominator there, because multiply to is not quite right. And the way you would do this is you would essentially multiply everything by the denominator 12. So multiply everything by 12, make it 7 equal to 3 times a plus 4 times b, and then you try and find numbers a and b that make that work. It's a little dicier here because there's lots of options for a and b. 1 and 1 is an obvious choice, but you could also do something like, I don't know, I'm not going to try and make up something else. 1 and 1 is the obvious choice, but you could make other things. Whereas what we're about to do, you will have 0 options. You'll have one option to get to the right answer, right? There'll be no other things that can end up happening once you see what's happening. Okay, so let's do this. So we're trying to integrate 2x plus 5 over x plus 2 times x plus 4. And the idea is we're going to take this fraction. So this part here is called the partial fraction decomposition. And notably, it has nothing to do with integration. We're just doing some algebra. We're going to take our fraction, our rational function, and we're going to write it as the sum of two simpler rational functions. Something divided by x plus 2 and something divided by x plus 4. Okay. There's a couple ways of managing this. The easiest way to do this is to then multiply everything by your common denominator that's on the left. So this is our first step, just writing down the partial fraction decomposition. And then the second step, we're going to multiply everything by the common denominator. Okay, so we're going to get, so you can certainly get to the point where you don't need to show your work for this. I'm going to show my work this time just to make sure everyone's on the same page, because I feel like people will get used to doing this a while, and then they kind of forget what they do to get there. And they're like, how do they get there again? So if you're not sure what you're doing from this step to the next step, you're just multiplying everything by that common denominator. The point of that being that we're not going to have any denominators. Okay, I think I need to borrow a pen. Try to make this one last as long as I could. It's all right. Take it. Thank you so much. Appreciate it. So, oh yeah, that's great. That'll work just fine. So the idea here, when you multiply this by this, the denominators cancel. And you just get whatever was on top, 2x plus 5. Over here, when we multiply x plus 2 times x plus 4 by the first term, the x plus 2's cancel. So you're left with a times x plus 4. When you multiply this by the second term, the x plus 4's cancel, and you're left with b times x plus 2. All right, so this next part is where I would be willing to bet your teacher's going to do a different thing. That's okay. The easiest thing to do, so there's kind of two routes you can take. You can either pick values for x to try and solve for a and b, or you can do this thing called equating coefficients. Sometimes you have to do the second thing, but I would always encourage you to, if you can, and you always can, pick convenient values of x first, and when you run out of them, then do the other thing that your teacher is probably going to show you. I'm not sure, maybe they won't, maybe they'll do the easy way. So when I say convenient values of x, I specifically mean values of x that make one of these two things equal to 0. That's a convenient value of x. Because these equations have to equal each other for every value of x. So if I pick something like x equal to -4 and plug that in, look what happens. I get 2 times -4 plus 5 on the left. I get a times 0 plus b times -4 plus 2. Or simplifying that, let's see, -8 plus 5 is -3 equal to b times -2. So b is going to equal positive 3/2. What's the other convenient value of x we're going to pick to find the other coefficient? Everybody. What makes the other thing 0? -2. We're looking for -2. So we pick x equal to -2. We get, so we plug in x equal to -2 for every x. So I get 2 times -2 plus 5 equal to a times -2 plus 4 plus b times -2 plus 2 is 0. That's why we picked it. So that goes away. That goes away. So I'm left with -4 plus 5, which is 1, equal to a times 2. So a is going to equal 1/2. Okay, we're not done, but we have finished the partial fraction decomposition. So then the rest of the problem is to go back and say, okay, this fraction is equal to 1/2 over x plus 2 plus 3/2 over x plus 4. So we're going to rewrite the integral as the integral of 1/2 over x plus 2 plus 3/2 over x plus 4. Which is then something we're able to integrate. So what's the integral of 1 over x plus 2? It's the natural log of the absolute value of x plus 2. So typically having just x plus a number or x plus or x minus a number in the denominator means you're going to get the natural log of that thing as your integral. You could break this up into many pieces. Like if you really, really wanted to, I don't think you need to, but you could write this as 1/2 the integral of 1 over x plus 2 dx plus 3/2 the integral of 1 over x plus 4 dx. You're certainly welcome to write that if you need to, but I don't want you to waste your time if you don't need to write that. We can see that, oh yeah, I've got a 1/2 times the 1 over x plus 2. That's going to equal 1/2 times the integral of 1 over x plus 2 is the natural log of the absolute value of x plus 2. 3/2, and then the integral of 1 over x plus 4 is the natural log of the absolute value of x plus 4. Let's see. So that is how we attack a problem like this. Just to be complete about this, cannot see the, I'm like, okay, I can see the time, all right. The other way someone might talk about solving for a and b here, just so you know what's happening when your teacher probably does it this other way. The other way people do this is they say, okay, well, these are polynomials that have to equal each other. When polynomials equal each other, the coefficients of like powers of x have to be the same. So what we do is a thing called grouping or equating coefficients. So my left side is 2x plus 5. And if I multiply my right side, I've got ax plus 4 times a plus bx plus 2 times b. So if I group the x terms together, I've got 2x plus 5 equal to ax plus bx, or a plus b times x. And the constant term is 4a plus 2b. And then they do this less efficient thing usually of saying, well, okay, if my x coefficients have to be the same, that means 2 has to equal a plus b. And if my constants have to be the same, that means 5 has to equal 4a plus 2b. And then I've got a system of 2 equations and 2 unknowns, and I can totally solve it. I maybe would do, sure, I would say that b equals 2 minus a, and then plug that in there and get 5 equals 4a plus 2 times 2 minus a, excuse me. And then 5 equals 4a plus 4 minus 2a. And then 5 minus 4 is 1, and 4a minus 2a is 2a. So a equals 1/2. And then plug that back in there and get b equals 2 minus 1/2. So b equals 2 minus 1/2, which is 3/2. You get the same numbers, it just is a different way of doing it.
If I'm remembering correct, I think the teacher just did the first way.
Oh, you guys already talked about this in class?
Yeah.
Oh, okay. Interesting. But your homework isn't done do it for this like forever, right? Okay. All right. Well, okay. So your teacher did this the first way we did it? Awesome. That's so here's what I'll say about that. That is what you should do until you can do it no more. Because there are probably going to be some problems where you have to use both. Maybe. Let me double check real quick here. Why is that so? Oh, darn it. Sorry, I just printed stuff out that it already printed out, which is not terrible, but it's kind of terrible. Let's see. Okay, yes, there will be some problems where you have to do both of these methods kind of combined together. Great. Questions about what we've done here before we move on to another example? Okay. So let's look at something else. Let's look at something like, and yeah, we're going to get into it right away. So let's say we want to do the integral of 3x minus 8 over x cubed minus 4x squared dx. Definitely doesn't look like a u sub is going to work here, because if I let u be the bottom, the derivative of the bottom is 3x squared minus 8x, which is maybe slightly deceiving. You might think that would work because you're like, well, it's just the top times an x, but having an extra x in there is challenging. It's not going to work out doing a u sub. So, right, I mean, you could write it down. U equals x cubed minus 4x squared. Du is 3x squared minus 8x dx. If I divide that, I'm going to have a leftover x in the bottom, and that's a problem. I can't really solve this. I can't really solve this for x and do a back sub. And my 4s look terrible. So, not going to work. But important to think about, because sometimes it will. So since that didn't work, it's definitely not integration by parts because I don't have a mixture, but I only have powers of x. I don't have any logarithms or exponentials or trig functions. So it's not a mixture. I'm not even thinking about integration by parts. I'm going straight to, well, can I factor the bottom? Because it is a rational function, and I can. I've got x squared times x minus 4. Yeah, sure. Okay. So we're going to do the partial fraction decomposition for 3x minus 8 over x squared times x minus 4. And here's what's going to happen. You may already know this. Any factor that's raised to a higher power, and you might want to think of this x as x minus 0 squared, just to think of it as, oh, it's a factor, it's x minus something, but it's raised to a higher power. You need that highest power of that factor and every lesser power as well. So when I do the partial fraction decomposition here, I'm going to have a divided by x squared, and then every lesser power as well, down to 1. And then I'm also going to have a c divided by the other factor, x minus 1. We'll say that in a minute. So then we're going to do the same thing we did before. We're going to multiply both sides by our common denominator. And this is why before I was saying these denominators don't actually multiply to that denominator. They just all are part of or factors of that denominator. So when I write this, I'm going to have, let's see here, multiply both sides by x squared times x minus 4. I just like to do this. Put it over there. On this side over here, that totally cancels out, and you get 3x minus 8. When you multiply it by a, the denominator is always going to cancel. We're just looking at what's left over. So I multiply x squared minus times x minus 4 by a over x squared, the x squareds cancel, and you get a times x minus 4. When you multiply by this term, one of the x's cancel, and you get b times x minus 4. And finally, when you multiply by this last part, you get c times x squared. Okay, so now we're going to pick some convenient values of x, and the convenient values of x are really always just the numbers that make this denominator 0. Yeah.
Okay, but why do you multiply by x squared times x squared?
Because that is my common denominator.
Oh, that's
Whatever is your original denominator after you factored it, or even if you haven't factored it, that original denominator is always what you're going to multiply both sides by. I'm not going to multiply by x cubed times x minus 4. I don't need to do x squared times x minus 4. I just need the least common denominator, which is x squared times x minus 4. So now you can actually look at this original decomposition to be like, oh, well, x equals 0 makes those denominators undefined, or makes those denominators 0, and x equals 4 makes that one denominator 0. So those are going to be our choices for the convenient values of x. So notably, we only have 2 convenient values of x, and we got 3 constants to solve for. Means we're probably going to run out. That's okay. So starting with x equals 0, I'm going to get 3 times 0 minus 8 equal to a times negative 4 plus b times 0 plus c times 0. So all I have is negative 8 equals negative 4 times a, or negative 8 divided by negative 4 is equal to a, or in other words, a equals 2. And then we pick the other convenient value of x, which is x equal to 4. So plugging in 4, I get 3 times 4 minus 8 equal to a times 4 minus 4 plus b times 4 minus 4 plus c times 4 squared. You don't need to write these terms. They're just zeros. So I have 12 minus 8, which is 4, equal to c times 16. So c is going to be 4 over 16, or 1/4. But now I have run out of convenient values. There's nothing else I can plug in for x that's going to make a bunch of things 0. There are 2 ways you can go from here. You can either, and if you only have one thing left to find, it's usually pretty okay just to pick any other value of x you want. So you could pick something like x equal to 1, and then plug in both your a constant value and your c constant value and solve for your b constant value. That's not the way I like to do it, but it is a way of doing it. The way I prefer to do it is to now at this stage equate some coefficients. So I always look for the highest coefficient. What's my highest power of x on either side of this equation? 2. So I'm going to look at the second power. So on the left, if I look at the coefficient of x squared, on the left-hand side, I don't have any. So I have a 0x squared on the left-hand side. On the right-hand side, if I were to multiply it out, I wouldn't get a times x squared because that's just a times x and a times negative 4. But I would get a b times x squared. So I have b times x times x. So I would get a b times x squared. And I would also get a c times x squared. So this tells me that b plus c has to equal 0 because the coefficient of x squared on the left has to match the coefficient of x squared on the right. So I get 0 equal to b plus c, and knowing that c is equal to 1/4, b has to equal negative 1/4. So b equals negative 1/4. That is my preferred way of doing it, personally. You could go the other way, though. You could have, if you really wanted to, said, I don't like that. I'm going to plug in x equal to 1, and then I'm going to plug in what a and c already are. So I would get 3 times 1 minus 8 equal to a, which is 2, times 1 minus 4, plus unknown b times 1 minus 4 plus c, which is positive 1/4 times 1 squared. And then you could solve that for b. That seems like a pain to me. I don't love that, but you could do it that way if you really wanted to. And you would get -5 equal to 2 times -3 is -6, plus b times 1 times -4 is -3b, and then plus a 1/4. So let's see, add 6, subtract a 4th, equals -3b. So b equals 3/4 divided by -3, which is going to be a -1/4, as we already saw. Either way is fine. I just feel like this is way more work than doing this. Also, if you have more than one constant left to find after you used up all your convenient values, doing it this way becomes much, much, much worse. Whereas equating coefficients usually still doesn't get too complex. So that's what I would say is typically equating coefficients is the way to go after you have used up all your convenient values of x. All right, now we still have to do the integral, right? We're not done. We did the partial fraction decomposition. Now we actually have to rewrite the thing. So all we're doing is we're taking our partial fraction decomposition, a over x squared plus b over x plus c over x minus 4, and doing the integral of that, plugging in our values for a, b, and c. So the integral of 3x minus 8 over x squared times x minus 4 is equal to the integral of, let's see, a was 2, b was -1/4, and c was positive 1/4.
Another thing our professor is having us do is find the integral before we find a and b.
Like, just be like, so, I mean, sure, that's okay. That's not terrible. I don't hate that. I mean, I see what they're getting at there. You don't really know so that's not bad. Like, it's weird, but it's not a bad thing to do. The point of that is that you don't really need to know it. Well, the only thing I would say about that, the one downside to that is if A, B, or C, if any of them happen to be 0, which sometimes they do end up being 0, then you've done work you didn't really need to do. Other than that, it's a perfectly fine thing to do. And I get the point. The point is that you can totally integrate this if you know, without knowing what the constant actually is. One thing I would make sure you're aware of is that if your denominator, if you've got a constant over just x to the first, or x to the first minus a constant, or x to the first plus a constant, you're just going to get a natural log. On the other hand, this part right here is not going to be a natural log, right? If your denominator isn't just x to the first, then you typically can just do the power rule by rewriting it as x to a power. So you want to be careful here and make sure you think of this as the integral of 2 times x to the -2nd. And then I have a -1/4 over x and a +1/4 over x minus 4. And that's going to equal, well, I know how to integrate x to the -2nd is 2 times x to the -1st divided by -1. And then the rest of this is just logarithms. I get 1/4 natural log of the absolute value of x plus 1/4 natural log of the absolute value of x minus 4. And if I was going to rewrite this, I would do one thing, maybe two things. I would for sure rewrite this as -2 over x, because that just looks better. And I will point out, because sometimes it comes up, you could compress these two logarithms into one logarithm. You could write this as, I'm going to factor out a 1/4 times this one first, because that's the positive, so natural log of the absolute value of x minus 4 minus the natural log of the absolute value of x. And then sometimes solution manuals will compress that and get a natural log of the absolute value of x minus 4 over x. That is a thing people do sometimes. And there's actually a good reason to want to do it on occasion when we talk about the next section, which is improper integrals. Yeah. No, it's 3 o'clock already. So I wanted to say, let me just say one last thing just to make sure I don't leave you all confused about something. So yeah, real quickly, I'll just point out that if we're not going to do it, but if you had to integrate something like 3x squared plus 5x minus 8 over, I'm going to make something truly heinous here, x cubed times x minus 4 squared times x plus 1 to the 4th. God, that would be terrible. So if you had to do this, which no one would ever ask you to do this, I just want to make sure that you're all clear on how the partial fraction decomposition works. So the way we would do the decomposition here is each of those linear factors, x, x minus 4, and x plus 1, you get each of those raised to their highest power, and then every power that is less than that. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces in my partial fraction decomposition. No one's ever going to ask you to do a problem like this, but I just want to show you how it works so that you understand what's going on. So for the x cubed, I'm going to get a over x cubed, and then every smaller power. For the x minus 4 squared, I'm going to get d over x minus 4 squared, and every smaller power down to 1. And then for x plus 1 to the 4th, I'm going to get f over x plus 1 to the 4th, and then every smaller power. Which is terrible, but that's what it would look like. No one's ever going to make you integrate or even solve something like this, but someone could ask you maybe something a little less terrible, just to how you would set up the partial fraction decomposition. And they want to make sure that you know that every time you have a linear factor raised to a higher power, you get that higher power and every lesser power down to 1. Cool. Let's get one. We should end it. Next time on Monday, because we don't have class on Friday because it's a holiday. I won't see you. Have a good holiday. Next time we'll talk more about this because I think there's one other thing we need to look at, but I'm not 100% sure. So I'll make sure. Let's see. I'll look right now. I don't think I see any examples where you have to do the other thing I'm thinking of, which is kind of too bad because it's kind of fun, but oh well. But we do have some partial fractions where we have to do polynomial division first. So looking at problems 8 and 9 on section 6.3, you definitely have to do polynomial division before you can do anything else on that problem. Okay, I'll leave it at that. I'll see you all in 5 days. Yeah, Monday. I'll see you all on Monday. On November, what, 14th? And that's Monday. Oh, yeah. Yeah. Thank you so much. I appreciate it.